So last lecture we finished with typical sequences. Let's just repeat what they are. To get this, consider a discrete memory source. This is a source with a finite alphabet x and independent and identical distributed random variable x. And if you look at a finite sequence xn, whose ith entry is xi, which takes values in x. And with naxn, we count the number of positions of xn having the letter a, if a is in x, and we intuitively expect that naxn is approximately n times px of a. Therefore, Shannon defined epsilon entropy epsilon typical sequences in this way here, that minus 1 over n log 2 pnx of xn is between h of x plus epsilon and h of x minus epsilon. This idea just comes from the weak law of large numbers. We serve our intuition is right, then we get exactly this definition here. If we define typical sequences in this way, we get the following theorem. We see that the probability that a sequence is typical is approximately 2 to the minus n times the entropy of x. The cardinality of the set of all typical sequences is approximately 2 to the n the entropy of x. And the probability that a sequence produced by the source is in the set of typical sequences goes to 1 if n goes to infinity. Then we look at another way to define typical sequences. This is called letter typical sequences. In this definition, we want to have that nax of n over n is between 1 minus epsilon times px of a and 1 plus epsilon times px of a. So like we have our intuition, again, px of a is approximately naxn over n. Also with this definition, we could prove a similar behavior. So if you look at the letter typical sequences and we look at the probability of xn, that's approximately of a typical sequence is approximately 2 to the minus n times entropy of x. The cardinality of all typical sequences is approximately 2 to the n, the entropy of x, and the probability that a sequence is in the set of letter typical sequences goes to 1 if n goes to infinity. Then we look at the first application of this theory. Our first application is source coding with typical sequences. First, we look at variable length coding without error. So the idea is that we have a source which output a sequence xn to the source encoder, and he have to encode it with a word w to the decoder, and the decoder estimated by x hat n of w. And if we want to do error-free decoding, then at the end x to the n have to be equal to x hat of n of w. The idea is that we assign each sequence in the set of typical set a unique positive integer. According to our expression, w can be represented by n times 1 plus epsilon h of x bits. That was exactly what we have in the theorem before. If a typical sequences xn is put out by the source, then the encoder sends 0 and followed by this number of bits represented by xn. Now what do we do if xn is not typical? Then the encoder sends a 1, and then we send the bits without any compressions. So these are n times log 2 x bits representing x to the n. And now we want to look at the rate. That's the expected length over n. So that's exactly this probability. So we write it's a probability that the sequence is typical times the expected value plus the probability that the sequence is not typical times the expected value. And we see that this part here, so the second part, goes to 0, and the first part goes to 1 plus epsilon h, the entropy of x plus 2 over n. So if n goes to infinity, that means we can transmit at any rate about the entropy of x bits per source symbol, as we expected. The second case we look at is block length coding with error. So in this scheme, we also have an error, but we want to have that the error is small. And the idea is the same in principle, or very similar. Again, we look at the typical sequences, and we know with high probability the source puts out the typical sequences. And again, we know that we can represent these typical sequences by n times 1 plus epsilon h of x bits. So if a typical sequence is put out by the source, then the encoder sends n times 1 plus epsilon the entropy of x bits, which represent xn. And now we accept a small error. So if the sequence is not typical, then we just send zeros here. So every time we cannot decode it if we have a non-typical sequence. And if we now look at the rate again, then we get the same result, that it goes to the entropy of x. But what is with the converse? Perhaps it's possible to compress better. So the idea is just to use Fanus inequality. Oh, it's not here, but the converse follows just by Fanus inequality. We just apply Fanus inequality to get the converse, and then we know that we cannot compress better, that this is the best possible way to do this. Then we continue with our definition. Instead of a sequence, typical sequence, we look at jointly typical sequences. That means we look at two sequences, xn and yn, and look at NAB, xn and yn. This is just the number of times the pair AB occurs in the sequence x1, y1 in the joint sequence until xn, yn. And again, we define it like before we define jointly typical. It's just a generalization of typical we have before, and we do it here for the letter typicality here. And then we see that the probability that our sequence is typical is approximately 2 to the n times the mutual information between x and y. The third typical thing is conditional typical. It's a little bit more tricky. Somehow it's defined as the output if we send it over a system. So the formal definition you can see here, and then we had a theorem, and we look at the probability of yn conditional of xn, and we saw that it's approximately 2 to the minus n, the entropy of y conditional on x. And we look again at the cardinality of it, and we saw that the cardinality of all conditional typical sets is 2 to the n h of y of conditional on x. And then we look at the probability of yn, that it's in the typical sets under the condition that xn is equal xn, small xn, that goes to 1 if n goes to infinity. And then we can look at the probability of yn, that it's in the conditional typical sets. It's approximately 2 to the minus n times the mutual information of x and y. Finally, we look at the mismatch typicality. This is just if we if we assume a wrong discrete memberless source. So we assume that we have a sequence xn, which is emitted by the discrete memberless source px, and we have px tilde, which is covered by px. Then we have the probability that xn is in the set of typical sets, but concerning x tilde is approximately 2 to the minus n, and then we have the relative entropy between px tilde and px. That was our final result.